Hi everyone, my name is Avijit and today I will be talking about our paper Subverting Fair Image Search with Generative Adversarial Perturbations. On the left, we see a screenshot of a Google image search result for the search query professor style. And we see that almost all of the results are white men in tweed jackets, which is obviously not how all professors look like, essentially showing a stereotype. On the right, we have a more recent result for the same query where we see professors of different skin tones, of different genders, of different clothing, which is more close to what the representation in the real world looks like. So essentially, one could see why fair image search is important, because the real world image search system not only has to crawl images from the internet, but it also should ideally present diverse and nuanced perspectives. So let's talk about how that's accomplished. So in the literature, there are different techniques for fair ranking. Interestingly, a majority of these techniques require the protected attribute information, which is like they require the information of the race or the gender of the people that are being ranked. Now, this is not something that's always available. And so a workaround for this is by operators to use demographic classifiers that infer the race or gender or other sensitive attribute either from their name or their zip code or their image. And we know from previous work that these third-party classifiers are not 100% accurate. And there was some work that we did earlier to see what these inaccuracies in these models, what the impact might be on downstream fair ranking. So what we found back then was that fair ranking methods, which do require access to this demographic information, are very prone to violate fairness guarantees if this information is noisy, like if these labels that are predicted are noisy. And sometimes protected groups can even be worse off, like certain groups after the fair re-ranking were actually worse off because their labels were all messed up. And the fair ranking algorithm actually made things even more unfair. And this sort of violation is not easy to predict because the relationship between per class prediction accuracy and the overall sort of effect is quite complex. So now, where does adversarial attack come into place and how can that cause even more bias? So let's talk about intentional biases. So in the previous work that I just introduced, I talked about unintentional bias due to pre-trained classifiers being inaccurate. But what if somebody made the demographic information untrustworthy intentionally by being an adversarial actor? So a paper from last year showed that the same adversarial perturbation added to images from different groups can cause very different machine learning model outcomes. So like the image of this Black woman with the perturbation added, her age is mispredicted, but the same algorithm does not get confused by the same perturbation added to the image of a white man. So what is the threat model that we used in the paper? So essentially, we attack a fair image search model, essentially something like I just described, a fair list of images that comes up when you search for something. So that consists of two parts. A retrieval step, which essentially from the entire repository of images grabs the most relevant images. And then a fair re-ranking step, which reorders these images based on some sort of measure or metric of diversity or fairness. The fair re-ranking step can either use labels or can use image embeddings. There are different techniques, and so on. The threat model we used is very realistic and also very, very restrictive to be as close to real-world attack as possible. This attack is completely black box. So what does that mean? So this is an evasion attack, which means that the attacker does not have access to the model parameters. The attacker also does not know which fair re-ranking system is being used by the image search system. So all the attacker can do is they can upload adversarially perturbed images onto the internet, and then the web scraper that collects clean images from the internet also collects these adversarially uploaded images and combines in the same repository. And that then ends up causing the unfairness in the ranking. So this sort of threat model is very similar to either clean label attacks. So this is how the attack looks like. So in part A, we see that there is an example search result. When somebody searches for the query tennis player, we see the search results having, people from different skin colors, different genders, and so on. So it's pretty diverse. In the center, we see that, there is a trained gap, which is a generative adversarial perturbation model that perturbs certain images to selectively misclassify them as certain groups. So in the example image, a light-skinned male is perturbed by the gap to be mispredicted as a dark-skinned man. And then these perturbed images go with all the other images crawled in on the internet to go into the corpus, which then goes into the retrieval model, which retrieves images from the corpus. And then it's passed to the fairness-aware re-ranker to re-rank these images. Now, because the image of the light man has been mispredicted as dark, the fairness-aware ranker actually thinks of this person as needing an algorithmic boost and pulls this person up to the top, which is actually unfair. And that's sort of the attack that's possible for an adversary to do. So let's look at now the different methods that we use to achieve this or to design this attack. So the first thing is the generative adversarial perturbation, or GAP. So the GAP, or the generative adversarial model, is essentially an end-to-end convolutional model. What it essentially does is to take an image, to insert a perturbation, and in such a way that the perturbed image would be misclassified by a pre-trained model. So like if there's a pre-trained model that, sort of predicts a person's race or a person's gender, this model will selectively enter noise so that that person's race or that person's gender label is mispredicted. Why we chose GAP is because it's a convolution, end-to-end convolutional model. It can actually deal with images of any size, any resolution, and so on. And once trained, we can use this to generate perturbed images very quickly. So it scales very well. And it's also close to real life, because in real life, you have images of all shapes and sizes. So we use two pre-trained demographic classification models. We use this model called DeepFace, which is a model developed and released by Facebook. Also, there is this model called Fairface, which is designed for race and gender inference. And this is also available freely from previous research on GitHub. The GAP was able to fool both the models, and there are more details in the paper. The next part of the setup is the retrieval model. So for the retrieval model, we use something called the multimodal transformer. It's from a very recent paper. So essentially, it's a transformer-based model, which it uses both a visual transformer and the text transformer, and it learns image and text embeddings together. So essentially, it allows the person, the practitioner, to enter a free text caption, and based on the embeddings learned, it surfaces images from a repository that have the closest embeddings to this input text. So it's very efficient and state-of-the-art. And the final piece of the puzzle is the fairness-aware ranker. So in the paper, we looked at two different fairness-aware rankers. The first one is DetConsort, which is developed and deployed at LinkedIn. So this algorithm actually requires protected attribute labels. So it requires the race or gender labels, and then it greedily sorts these people based on some target distribution to move people to the top. The second algorithm we looked at is fair maximal marginal relevance. This is, again, developed and deployed by Shopify. So this works slightly differently. It uses image embeddings to form clusters. And the way it works is it will pick the next image based on the embedding information, so that it maximizes the relevance of the next image in the search result, but also minimizes similarity. And it minimizes similarity in the axis of either race or gender or whatever we pick. And this method does not require access to demographic labels, because it only uses the embedding information. So in theory, it should be harder to fool. But in reality, we find that both these algorithms were actually performing very poorly under the adversarial attack. So what are the experiments we did to verify that our attack works in a variety of different scenarios? So the data set we used as the retrieval data set were and skin as skin color and gender annotated subset of Microsoft Cocoa. We only use the images that had people and specifically one person. So this amounted to 8,692 images. The search queries we used were 3 different search queries. These were based on the most common terms, query terms present in the captions of these 8,692 images. We used 2 different attack training models. So the demographic models used to train the gap. We used deep face and fair face, I already told you. We used 4 different training objectives, like any person mispredicted as a light man, or light man mispredicted as anyone else, only dark man mispredicted as light man, only light man mispredicted as dark man. We use different attack probabilities, which is the fraction of images that are adversarially modified in the query output. So suppose the query returns 100 images. We either modify 20% of the images, or 50%, or 70%, or all of them. And top K is the length of the search list that we get. So under these different scenarios, what do we observe? So we look at a few different metrics. So we look at representation, which is skew, which is whether or not a group is overrepresented or underrepresented. That's what skew measures. We measure attention, which is the amount of visual attention that every group gets or every person gets, going from top to bottom. And we measure ranking quality in terms of NDCG, which is pretty popular in IR literature. We specifically wanted to measure the boost conferred to the majority subgroup in the dataset. So the subset of Cocoa that we have has majority light men. So we wanted to see after an attack, how much boost in the metric did light men get as compared to the worst affected subgroup. So we wanted to measure the maximum range. We will now talk about the results of our study. So the first thing that we observe are that the skew and the attention generally unfairly increases towards light men as a result of our attack. Essentially, light men were both getting overrepresented in the top K and also getting more visual attention as a result of the attack. And the probability or the strength of this attack increases as more and more percentage of the output query list was perturbed. Interestingly, we also observed that the ranking quality actually does not change by much as a result of the attack, which means after the attack, the images in the top K were still relevant to the query, but they were mostly of light men. When it comes to the training model that we use to train the gap model, the adversarial perturbation model, we see that the attack was successful whether or not we use deep face to train the gap or fair face to train the gap. So it was equally capable of fooling both of these pre-trained models and also ending up conferring the attack on the embedding-based FMMR model. Finally, we observed that no matter what the training objective was, which is you modify everybody as light men or you modify light men to anyone else or so on and so forth, we saw that the majority group, which is the light men, were getting unfair boosts no matter what the direction of this misprediction was. This is something we looked at more deeply in the paper, and due to lack of time, I will not be discussing it here, but I request you to look into the paper as to why this was happening. So to conclude my talk, we see that the attack that we have described in this paper can successfully cause a lot of unfair advantage to people from the majority class, which were light men in the paper, both in terms of representation or attention and so on and so forth. We also see that the attack is robust because we looked at a number of different variables, like we changed the query, we changed the training algorithm, we changed the fair ranking algorithm, we changed the length of the search list and the fraction of images that were modified, and the attack was successful regardless or throughout. So this attack is quite powerful. The attacks are also stealthy. That is, they have very close to zero impact on the search quality. Like the search results remained relevant, but also because the pixel perturbations are invisible to the human eye, they were stealthy because it's very hard for a human being to catch that this sort of an attack was happening. We obviously did not test this method on a real life system because we don't have access to a real life stack of either LinkedIn or Shopify or Google, but we think that this might be possible. And with that, I conclude my talk. I request everyone to read the paper and leave questions or comments for me or any of the authors. Thank you.